In this presentation by myself, Camden, and Aditya, we will apply General Chemistry 1 topics to discuss the chemistry of chlorofluorocarbons and their impact on the ozone layer of our atmosphere.
Our story begins with ozone itself, a compound made of 3 oxygen atoms. There are 2 types of ozone, both ozone at the ground level, which is considered bad, and ozone in the stratosphere, which is considered good. For the purposes of our story, however, we will focus on the good ozone, a part of the atmosphere that largely serves to protect the Earth's inhabitants. The ozone in the stratosphere is formed through photolysis, otherwise known as the separation of a molecule by light. And this good ozone absorbs UV radiation from the sun. On this slide, we have also listed some implications of ozone depletion today. But to truly understand these, as well as to comprehend the chemistry between how ozone works to protect us, we must first understand ultraviolet radiation.
Structurally, UV light is simply the portion of the light spectrum with extremely low wavelengths. The sun emits this UV radiation and it travels far distances to eventually reach the Earth. Since we know the relationship between wavelength and frequency, we can thus conclude that it has the highest frequency and resulting penetrative ability. UVB rays specifically, the intermediate UV light form, have a wavelength between 280 and 315 nanometers, and therefore a very high frequency. Thus, we can see the results of ozone depletion in the effects of UVB radiation, which spans from increased precedence of certain types of deadly skin cancer to the widespread death of crops and marine life. This also further shows us the importance of this global issue in each of our daily lives and why understanding the chemistry behind CFCs and ozone depletion is crucial.
Now that we have learned a bit about one of our antagonists, UV radiation, we can shift our attention back to our protagonist, now striving for a deeper understanding of the molecule itself. Ozone, as we mentioned previously, is formed by the process of photolysis, one that occurs in 2 steps. First, a UV light wave breaks an oxygen molecule, which is naturally diatomic, into individual oxygen atoms. Each atom then collides with another oxygen molecule to generate ozone. Ozone itself is composed of 3 oxygen atoms, 2 of which are peripheral oxygens, each covalently bonded to the central oxygen atom. This molecule exists in 2 different resonance structures, each aligning the central oxygen atom a +1 formal charge and attributing a -1 formal charge to a different peripheral oxygen atom. Ozone also has a bent molecular geometry and a bond order of 1.5. Through its structure, in which it shares 4 electrons among 3 nuclei, and because of its electrons' high potential energy when arranged in their natural state, ozone is also highly reactive with other atmospheric compounds. This quick breakdown of the elements and compounds present in our atmosphere shows us that stratosphere-level ozone, although an extremely vital portion of our atmosphere which protects us from harmful UV radiation, only makes up about 0.000007% of the atmosphere. This seemingly minute percentage is likely attributed mostly to the set of reactions required to create ozone, as we learned about in the last slide, and its high reactivity with other atmospheric compounds.
In the past few slides, we have thoroughly educated ourselves about the chemistry behind both ozone and ultraviolet radiation, and each of their respective roles both in Earth's functioning and in the atmosphere. Now, we will learn about how us humans impact this natural order through our wasteful consumption of certain substances called fossil fuels. By definition, fossil fuels are substances formed from the buried remains of dead plants and animals that once lived on Earth. Because of their biological origins, these substances are high in carbon makeup and usually contain hydrocarbons, another compound that we discussed quite often in class. An example of how these substances are used as fuel can be seen in the combustion of coal, another chemical reaction similar to those we learned in class, in which coal is combined with oxygen to release water and carbon monoxide. This reaction generates quite a bit of energy, around 100 plus kilojoules, and is thus functionally a good way to produce energy. The side effects, however, are not as pleasant.
One of the side effects of our consumption of fossil fuels in our daily lives is the release of greenhouse gases into our atmosphere. These gases are defined as the products of reactions that happen when humans burn fossil fuels. Essentially, they're a recombination of the fossil fuel and oxygen that creates an unfavorable compound, which is then released into our atmosphere. Greenhouse gases cause an effect that is crucial to this presentation, the greenhouse effect. That is something that almost everyone has heard of in daily conversation, and is defined as the warming of the Earth's near-surface atmosphere through the trapping of the sun's heat by greenhouse gases. Essentially, as the stratosphere, which is the atmospheric layer that houses good ozone, is cooled, the near-surface atmosphere is warmed. Some greenhouse gases formed from the consumption of fossil fuels fall under the category of chlorofluorocarbons, or CFCs. These gases create a kind of super greenhouse effect because of the strength of their absorption bonds, the bonds that dictate how much of the sun's heat they can absorb and therefore trap into the atmosphere. A pattern can be seen in which chlorofluorocarbons with higher molar mass are more effective as greenhouse gases in increasing global warming as compared to other greenhouse gases such as carbon dioxide, which is present at near saturation levels in the atmosphere and thus exerts less force or less power for its molar mass.
Studies indicate that CFCs are not naturally chemically synthesized in nature and are therefore a direct product of human consumption of fossil fuels. This itself is astounding and provides perspective on how much we have truly landed ourselves in this environmental crisis. This began when humans synthesized CFCs to be used in refrigerants and aerosol propellants. Structurally, chlorofluorocarbons, as the name suggests, are composed of fluorine atoms, chlorine atoms, and carbon atoms, all linked together by covalent bonds. Although the individual covalent bonds in these compounds are highly polar, many of the dipole moments tend to cancel out, and the resulting molecule itself is lacking in ionic character. This makes it especially dangerous as it does not dissolve and is therefore unable to be removed from the atmosphere through naturally occurring deposition. Some other notable properties of chlorofluorocarbons include low toxicity, a property meaning that it does not directly hurt humans and was likely a reason we synthesized CFCs in the first place, low reactivity, meaning they will not easily react with other compounds and recombine with their constituent elements, and low flammability. Now, the question arises, what makes CFCs different than other greenhouse gases? First, just as many other greenhouse gases do, CFCs introduce carbon into the atmosphere and increase its proportion and abundance. More importantly, however, CFCs also break down when exposed to sunlight and release free chlorine into the atmosphere, where it interacts with ozone.
When ultraviolet waves strike chlorofluorocarbons, the bond between carbon and chlorine is broken by the energy of the wave, and the chlorine atom is freed from its initial compound. Next, this free chlorine atom strikes the ozone molecule and breaks an oxygen-oxygen covalent bond, resulting in the creation of two separate molecules, oxygen and chlorine monoxide. Free oxygen strikes chlorine monoxide molecules to generate free chlorine, which starts the process all over again. This series of chemical reactions and its analogous graphic beautifully illustrates the danger of chlorofluorocarbons and their potency in today's atmosphere. One single chlorofluorocarbon molecule can repeat the same cycle 100,000 times and destroy many, many ozone molecules. This fact, coupled with just a 0.000007% abundance of ozone in the atmosphere, means that CFCs can truly break down a significant portion of the ozone layer.
It is not only the direct interaction between CFCs and the ozone layer that increases ozone depletion, however. As a super greenhouse gas, CFCs are responsible for the warming of the near-surface atmosphere, known as the troposphere, and thus is established by Drew Shindell at the Goddard Institute for Space Studies, the cooling of the stratosphere. The stratosphere has thus been projected to cool by roughly 8 to 10 degrees Celsius. So as 90% of atmospheric ozone exists in the stratosphere, This poses a real threat to the ozone layer as well, due to the fact that ozone, as a highly reactive compound, destabilizes at low temperatures. This is significant because CFCs not only prove to be a direct threat, but also an indirect one as well in their greenhouse gas nature.
Now that we have thoroughly covered the chemistry behind ozone depletion, it is also important for us to understand the policy behind CFCs. Originally, these compounds were considered safe, even miraculous, because of their properties, and once the dangers were realized, nothing was done. We have seen in Congress over the years that lawmaking bodies tend to be resistant to making big changes, and this was the problem in the case of CFCs. For a long time, it was difficult to find good alternatives to CFCs, and lawmakers simply did not give it enough attention. When CFCs were finally banned by the 1987 Montreal Protocol, even this was not enough. First of all, much of the damage done by CFCs was already largely irreversible or very difficult to correct. Also, fossil fuels are still burned very often, and suitable alternatives have not yet been implemented on a global scale.
To conclude, it is imperative that each of us realizes this is truly more than just a presentation on chemistry. Global warming is a real issue and will affect real people. In fact, it will affect each and every one of us. There is a global need now more than ever for the recognition and fixation of human impact on the environment. The time for action is now. We must decrease the use of CFCs and decrease the burning of fossil fuels, striving to use alternative energy forms in our own daily lives so that we can make a small but tangible difference in the fight against global warming. Thank you for watching our presentation.